Afternoon, Dr. Tran.
Hey Steven, how's it going?
Not too shabby.
Almost there. Almost Christmas times.
How much senior design stuff?
Uh,
How's it going, Dr. Tran?
I'm good, hanging in there. Almost the end of the semester. How are you doing?
Just stressed.
I know,
Hanging in there as well.
I'm hanging there.
It's crunch time right now for senior design.
I bet, yeah. What do you guys have to submit by the end of this? You have to do like a final presentation or like a design
Uh,
proposal?
Right now, we scheduled a meeting with Dr. Mayoral. So we're meeting with him on Thursday
Hmm.
for our critical design review.
Okay,
So after that, if it looks good, he'll give us the design freeze. And then from there on, we got the go ahead to work on our proposed designs.
cool, cool. Well, hoping for the best.
Thanks. So are we. How's your weekend?
Uh, it's good. Um, you know, busy but good.
Yeah, I feel you. Oh, I do have a question about the final report. Maybe I can show you later after
Okay,
class.
okay. Or you can ask now if you want, or we have some time right now.
Okay. Yeah, sure. Well, I'd like to at least show you my screen about it.
Oh, okay. Yeah, let me go ahead and swap that. It's not important anyway. Okay, go for it.
Yeah, let me open my stuff first. Okay. Starting mechanical. Still loading. Give me a second. All right, there we go. Oh, I cannot share at the moment.
Oh, sorry about that.
No worries, that's fine.
All right, go for it.
Okay. Oops, screen one. There we go. Yeah, I was working on my sled design for the team rocket team's avionics sled. This is
Okay.
basically supposed to hold our electronics, and for me, I set up some parameters. I wanted to ask you if this is a good idea.
Okay.
I applied a boundary condition for the fix on the top and bottom, since this whole thing will be fixated by these threads over here, as you can
Okay.
see. So that'll hold it in place.
Okay.
And I enacted a Earth gravity force. As it's going to be launched, it'll shoot upward.
Yep.
And I was wondering, like, what would be my best way to supply the amount of force? Would it be a force by acceleration or just the force by the rocket thrust? Right now, I have it based on acceleration, but the force I do have existing right now, I currently have it suppressed.
I honestly I think the acceleration, I think it does exactly kind of what you say,
Mhm.
but I like to basically apply an upward acceleration, what the force would be required for that. And I'm guessing you're applying it for the entire body, right? for the
Yeah.
acceleration.
Yeah.
I personally have not experimented that much with the acceleration, and so you know, I would lean more towards the force just because that's kind of what I've how I've usually done these things. Um, have you compared the results? So do they look similar when you do one or the other one?
Yeah, they're very small in nature,
Okay.
so I'd say it's pretty much similar
Okay, okay.
because
Yeah,
the
if they're pretty similar, I would
just stick with the force.
see the thing is I think with this one, the more accurate thing would actually be the acceleration because that's kind of what it's actually doing. And so if visually you're not seeing that big a difference between the results between the two, I would actually go with the acceleration actually.
Okay.
Just because that's kind of what's more you know, that's
Realistic.
what's more realistic of, you know,
Yeah.
intuitively that's what I would do. I mean, if a knowledge of all things, that I would choose an acceleration on this. It's just that I haven't personally you know, used it all that much.
Right.
I think for your case where you know this for your application, I think acceleration makes more sense intuitively.
Alrighty, cool. Yeah, because like yeah, the deformation, it's stupid small. And I expected this to survive that amount of acceleration either way because
Okay.
of the
Yeah.
raw calculations that we had to do for senior design.
Okay, yeah, that makes sense. I mean, yeah, it shouldn't be. I mean, hopefully something like this shouldn't break just because the whole rocket is accelerating. So this all makes sense.
Right. Cool.
Okay, yeah, looks good.
Awesome. Thank you.
Yep.
One more thing about the project. I want to ask about simple modeling. What do you mean by that again? Can we get like a refresher?
Right. So the simple model is basically a way that you're going to use to validate or verify your results. So and so I don't want you to just rely on finite elements to get your solution, because in reality, you know, you're always double checking the finite elements against something else. And so the best thing to check against would be some kind of like experimental data, like if you ran like a physical test on your geometry. But probably the simplest thing that you can do is just doing like a hand calculation, like simplify this as much as you can, so that you can, you know, you can calculate this by hand. Like what I like to tell people is, you know, think about how you would solve this problem, or think about how you would design this before you took this class, and think about what kind of calculation you would do in order to do that.
So for my case, could I use like a buckling scenario? Because
Oh yeah, you could.
typically-
Yeah, that's one thing. That's one thing you can do. Yep.
Okay, cool. Because I was also reviewing the rubric for that, and I saw that you also mentioned that like another alternative would be using the method that we did during the midterm.
Yes.
Yeah.
That's another option too. So you can do that as well. But you know what for every project something different is going to make more sense. And so, you know, you know, you got to just kind of choose which best one.
Okay, sounds good.
Close should our calculation speeds are at this?
Honestly, they're probably not going to be that close, just because because I know a lot of you are working on pretty complex finite element models. It's going to be really hard to get a hand calculation that can match that kind of exactly with geometry.
Say like 85%, like similarity is pretty close.
That's pretty close. Yeah, that's really close actually. So they're only 15% different from each other.
I think so, yeah.
That's really close, actually. That's really good. And so, like for a lot of projects, you know, I expect them to be not even close, because you know you have to make a lot of simplifications to the geometry. But you know, the point I want you guys to do is you know, just to get into the habit of, you know, I have to check my finite element results against something. In reality, you know, if you're doing this with a company, you're going to have a lot more resources available to you. But it's just a good mindset to get into to check your finite element results. And so that's why I have it as part of the project. Yeah. Okay, it's 5:30, so let's go ahead and get started. All right, good evening, everyone. How's everyone doing today? Good, hanging in there. I know it's the last week of class, so it's I know everyone's really busy, everyone's really tired, but you know, we're almost there. We just have a little bit more to go. Okay. All right, so the plan for this week is we're going to cover all the miscellaneous topics. Okay, so last week I put out a poll and to have you guys vote on the topics that you want to see in the lectures for this week. So thank you everyone who voted in the poll. And I took a look at the results right before lecture today. And the top three topics that that won were heat transfer simulations or thermal simulations. Number 2 was fluid mechanics or CFD, and number 3 was design optimization. Okay. So I don't think we're going to get through all of them because actually all 3 of these are actually really beefy topics that that are actually going to take a little bit of while to explain. But I should be able to get through 1 and 2 at the very least today. Okay. And if you're interested in design optimization, then of course all the notes for that are online already. And I have like an activity for that as well that I had my grad students do. But if you're interested, you can do it as well. Okay. But we will get through thermal. So that's the plan for today. We're gonna get through thermal simulations, and then we're gonna do fluid mechanics probably on Thursday. Okay. All right, so before we start today, I do want to remind you guys to do your SOQs, okay? So the SOQs, you guys probably know this at this point, stands for Student Opinion Questionnaires. And so that's your opportunity to evaluate me and to evaluate the course on how well the course is working for you, okay? And so the SOQs are really important to me. I know probably every single instructor says that, but I will tell you that I go through and I read every single comment and I see every single score that you guys give for the courses, and I take that feedback to heart. Okay, and so I've been here for a decent amount of time now. This is my 6th semester here, and so I used to say that, hey, I'm new here, I'm still trying to figure things out, but I have been here for a while. But that I think that doesn't mean that I don't have more to learn. Okay. And so I've always believed that, a lot of, especially something that you're professional at, it's a lifelong process of learning. And for me, the most useful, best way that I can improve my teaching is from hearing feedback from you guys. Okay. And the primary way that you guys give me feedback is through the SOQs. So, so please make sure you fill out those SOQs, and please be honest. I've had people curse me out in the SOQs before, and it doesn't hurt my feelings. Okay. And in fact, the people that have cursed me out before, that's probably the most useful feedback I've gotten on the SOQs. So please go fill those out. I don't want to take any class time for you guys to do it, just because we have a lot to cover this week. But please make sure you do it before Friday, because I think that's the deadline. Okay. Okay. Right. So that's all my announcements. And so are there any questions I can answer before we get started? Okay. All right, so let's go ahead and talk about heat transfer simulations. So heat transfer, I'd say heat transfer and fluids are probably the most popular miscellaneous topics. The unfortunate thing is, we spend the entire semester talking about structures, and heat transfer and fluids are kind of a whole nother domain entirely. And so, and so the reason I have my iPad out right now is that we have to do a little bit of review of heat transfer, just so that we can understand all of the essential concepts and all of the terminology for the boundary conditions. So has everyone taken heat transfer, or are some of you planning on taking it next semester as well? Next semester, okay. So I think there's probably a mixed bag of people have taken before, people haven't taken it yet. So no matter where you are in your heat transfer, I think this lecture will be useful because it'll kind of review a lot of really core concepts of heat transfer. Only really the ones that you need to run simulations. Okay. All right, so let's do heat transfer review. Okay. All right, so I actually, let's start by talking about why we can solve heat transfer problems in finite elements in the first place, right? And so if you think back to the very beginning of the class, right? So we talked about finite elements as just a general methodology for solving differential equations, okay? We've mostly just been focusing on one differential equation, which is the structural one, but heat transfer has its own differential equation as well, okay? And that equation is called the heat equation, okay? In my opinion, the best named equation in all of engineering. It's not named after some random scientist dude in the 60s or something like that, or the 16th century. And so the heat equation, in the most general form has something like this. Okay? And this is, of course, the 2D version, but there's also a 3D version as well. Okay. Okay. And so we have this kind of big differential equation here. Okay. And even though this looks really intimidating, and I'm being very careful saying this, so don't go to Dr. Banks or anyone or Dr. Wang and say that and repeat this, but in terms of difficulty, the heat equation is actually easier to solve than a lot of other differential equations. So it's certainly easier to solve than the structural equation, and it is easier to solve than the fluids equation. But again, don't let that comment leave this room. Otherwise, I'm gonna have a lot of angry heat transfer professors after me. You can tell that to me, but not to other people.
It's going on your SOQ.
That's okay. Dr. Banks and Dr. Wang don't read my SOQ, so that's fine. All right, and so there's a lot of terms here, okay, but the essential thing that I want you to take away from this is that what we solve this equation for is temperature. Okay. Okay. And the temperature, of course, is big T right here. Okay. Right. And so this tells us that when we solve a thermal finite element simulation, our primary solution variable is going to be temperature. Okay. And so if we compare this to our structural simulations, right? So in structural FEM or structural equations in general, our primary equation variable there is the deformation. Okay. Okay. Right. And so because our equation is so different and because of what we're solving for is different, of course, the way that we're going to set up the FEM is going to be different as well. Okay. And so it can be intimidating because I think the terminology and and the concepts of heat transfer, of course, are very different from structural. But I'm going to show you today that you actually have already I would say 75, 80, 85% of the knowledge that you need to run a heat transfer FEM, okay? Because at the end of the day, it's still a finite element simulation. And so you're still gonna need your geometry, you're still gonna need to mesh, you're still gonna need to apply boundary conditions, and you're still gonna need to view the results, okay? So all of those things are not gonna change. And so the only thing that really changes is, what constitutes, what types of boundary conditions that we apply and how we actually view the results. But even then, there's a lot of parallels that we can draw. Okay. Because remember, when we talked about boundary conditions in structural FEM, we talked about boundary conditions that are either constraint type boundary conditions and load type boundary conditions. Okay. And so thermal simulations actually have the exact same concepts. It's just, what we consider a constraint and what we consider a load is different because, we have a thermal simulation, okay? And so what I'm gonna go over next is, basically we're gonna go through the whole process of how you would actually set up a thermal simulation, okay? And we're gonna focus most of our attention on the boundary conditions because that's the main thing that's gonna be different, okay? Okay, any questions on this? Okay. All right. Oh, I guess before we get into that, let's talk about just kind of generally what you expect from heat transfer, kind of in general, because I know not everyone's taking it. Okay, and so in concept, heat transfer is not a difficult concept to understand. And if you've taken me for heat transfer, I know there's probably a couple of you in the class. You probably heard me say this too, right? And so the whole class of heat transfer is really centered around one central idea, is that heat, which is the same thing as energy, okay? Right, so heat is just a form of energy. Heat will go from hot stuff to cold stuff. Right? And so you have a surface that's hot and a surface that's cold. Heat is going to go from the hot thing to the cold thing. Okay. That's all heat transfer is. Okay. And so, when I teach heat transfer, I say this, that's like the very first thing I say in the class. And I say, we don't have to take the rest of the class. You guys understand heat transfer. Okay. That's not true, of course, and so the whole point of heat transfer is to say, how much heat is going through, and and all the nuances of geometry and types of heat transfer and yada yada yada. But if you understand kind of this basic concept, then you're going to have a great intuition for heat transfer. Okay. But again, don't tell Dr. Banks, don't tell Dr. Wang I said that. Okay. And so let's go through how we actually set this up in finite elements. Okay. And so let's start with the I think the easiest thing to talk about, which is the geometry, the connections, and meshing. Okay. All right. And so the great thing about this is that the exact same process that you follow for loading in your geometry, for meshing your geometry, and defining connections if you have an assembly of parts, all of this is exactly the same as your structural FEM. Okay. Okay. And so you guys have probably done this dozens of times in this semester. And so if you want to run a thermal simulation, this part is not going to change. Okay. The only small difference here is that because we're doing our equation is different. We're solving the heat equation instead of the structural mechanics equation. This gives us a little more flexibility in terms of the types of elements that we can use. Okay. And so in particular, for thermal simulations, it really doesn't matter all too much if you use a linear element or a quadratic element. Okay. Okay. I mean, granted, you're still going to get a higher amount of accuracy with a quadratic element, but you don't have any kind of extra issues. So you don't have like shear. So there's no shear locking in thermal simulations. Okay. And so it's perfectly fine to use linear elements, and actually, in fact, a lot of softwares actually do have this as the default. Okay. And so since you don't have to worry about shear locking, you can choose to use either linear or quadratic elements. But with that said, because ANSYS it's so easy to do quadratic elements in ANSYS, a lot of times it's still kind of preferable to use quadratic elements. But if you have some reason to use linear elements, maybe you need a particular high amount of mesh density in a certain area. That's a little bit easier to do with linear elements versus quadratic without kind of driving up your cost too much. Okay. But most of the times, I would say still stick to quadratic, but it's not a backbreaking issue like it is in structural mechanics. Okay. Okay. So besides that, everything is still the same. So you're still going to need to do meshes and geometries and all that stuff. Okay. So now let's talk about the boundary conditions. And this is where I think the biggest differences lie. Right. And so because, we're solving a whole different equation, we're not going to have things like fixed supports and forces and pressures and any of that stuff. Okay. And so we're going to have thermal boundary conditions instead. And so I'm going to make a list here of the most common ones that most people use in their thermal simulations. But of course, there's more options than this available in ANSYS. Okay. Right. And along the way, I'm going to draw some connections, some analogies back to our structural FEM, just to kind of help solidify these ideas. Okay. All right. So the most basic type of boundary conditions you can use in thermal simulations is a temperature boundary condition. Okay. And so with the temperature boundary condition, you're going to directly specify the temperature at a particular surface or a particular location. Okay. Right. And so, let's say that you're running a thermal simulation on a particular part, and one part of the part is going to be held at a constant temperature, right? And so, you say maybe that temperature is matches the room temperature, and so maybe it's around like 25 degrees C, or maybe it's really hot, and so it's 100 degrees C, right? And so you can directly specify the temperature at a particular location using this type of boundary condition. Okay. All right. And so this boundary condition right here draws a direct analogy to our structural simulations, because this is exactly the same as a constraint type boundary condition. Okay. Okay. Because remember what the definition of constraint type boundary conditions are, right? So constraint type boundary conditions, they directly specify the solution variable in your problem. Okay. And if you look back at the heat equation, right? Remember the thing that we're solving for directly, or the primary solution variable, is exactly the temperature. Okay. And so if you compare this to our to our structural cases, in structural FEM, remember, the types of boundary conditions that we consider constraints are things like our fixed supports, or things like our displacement boundary conditions, right? And so in all those types of boundary conditions, we directly specify what the deformation is like at those locations, right? So for a fixed support, we set the deformation equal to 0, okay? And for a displacement boundary condition, we set the deformation to be whatever it needs to be, okay? And so temperature works exactly the same way, okay? And so you can think of the temperature boundary conditions as a constraint type, okay? And along with being a constraint type boundary condition, this tells you that this is you usually need at least one of these in order to run a valid simulation. Okay? And so just like in structural FEM, you can't run a simulation without a fixed support. For a lot of thermal simulations, you can't run a thermal simulation without a temperature boundary condition. Although there are some exceptions for this, specifically with regards to convection and radiation, but we'll get there. Okay, any questions on this? Okay. All right, so that's temperature. The next type of boundary condition that we'll go over is a heat flow or a heat flux. All right, and so with these types of boundary conditions, you can specify the amount of heat or the amount of energy that passes through a surface at any given time. Okay. And so the units, the typical units that that are used for heat flow or heat flux are either watts. Okay. Watts for heat flow. Okay. Or the other unit for heat flux is watts per meter squared. Okay. All right. And this is nice too, because these also kind of have direct analogies to our structural FEM. Okay. And so a heat flow boundary condition, which has units of watts, this is analogous to our force type boundary conditions. Okay. Okay. Whereas the heat flux, which is a watts per meter square, this is analogous to pressure. Okay. Right. And so what this tells us is that, because these are analogous to force and pressure, a heat flow or a heat flux boundary condition is essentially a load type. Okay. Okay. Right. And so just like, in structural FEM where, our forces and pressures are our loads, then, our heat flow and heat flux boundary conditions, these are our, you can think of these as our thermal loads. Okay. And so remember with load type boundary conditions, the structure will, or in this case, the geometry will react to what the loads are applying. Okay. And so thermally, the way that you can think of this is that, if you specify a certain amount of heat flux going into your surface or into your geometry, the way that your geometry is going to react is by raising the temperature, right? And so the temperature of the device or the temperature of your geometry is going to react to how much, energy you're pumping into it or taking out of it. Okay. All right. And so I think this is probably the boundary condition that people have the hardest time using, because it's a little bit hard to kind of envision how you actually use this. And so I'm going to give you a couple examples of how you can use this, right? And so typically, if you're going to supply a heat flow or heat flux boundary condition, these are useful for cases when how much energy is passing through a certain surface. Okay. Okay. And so one example of this is, let's say that you're doing a thermal simulation on some kind of combustion engine. Okay. Very, very, very common application. Right. And so, of course, if you're simulating a combustion engine, one of the biggest sources of heat, in the engine, which is the primary reason a combustion engine heats up, comes from the combustion reactions that take place in the combustion chamber, right? And so in your combustion chambers, you mix, fuel, you mix oxygen, you ignite it, right? And so it's going to cause a chemical reaction to take place, which is going to release a ton of energy in terms of heat, okay? Okay. And so, if you want to see, or if you want to simulate how much your engine is going to heat up as a result of these combustion reactions, you can apply a heat flow or heat flux boundary condition, inside those combustion chambers. Okay. And so this is usually a lot easier than applying a pressure type boundary condition. Okay. Because usually if you have some kind of combustion reaction, so usually exactly how much oxygen is going to be inside that chamber, how much fuel is going to be in there, how much air is going to be in there, right? And so you can use chemistry to determine, how much energy that reaction is going to release. Okay. And so based on that amount of energy that's being released, you can then apply that as a heat flow boundary condition on the walls of your engine, and then have your engine heat up as a result of that. Okay. And so in cases where you have good knowledge of the amount of energy that's either being produced or that's being released, then a heat flow or heat flux boundary condition is a great option for that. Okay. But I think what's really hard is that if you have a combustion reaction taking place in a tiny combustion chamber, it's really hard to determine what the exact temperature is going to be inside there, unless you have like a thermocouple or you have some kind of thermometer inside the chamber, which most cases you're not going to. And so in this case, you have a much better idea how much energy is being released, and so just apply that as a boundary condition instead. Okay. All right. And so in the same vein, another useful case where you can use a heat flow or heat flux boundary condition is if you have some kind of electric heaters. Okay. And so most electric heaters, if they were made somewhat recently, have a rating of how much power that they can operate at, right? And so that power rating is an expression of basically how much heat is being released into the room. Okay. And so again, if you have knowledge of how much energy or how much power a certain device is outputting, you can use that as a heat flow heat flux boundary condition on your simulation. Okay. And so let's say that you want to run a simulation that's going to simulate the temperature distribution inside this room, where if we have like a floor heater on that side. Okay. And so the type of boundary condition you would apply on the floor heater would be something like this heat flow based on the power or the wattage of that electric heater. Okay. All right. Any questions on this? Okay. All right. Number three is not really a new boundary condition on its own. It's more of a special case of the last one. Number three is what's called a perfectly insulated boundary condition. Okay. And so perfectly insulated boundary condition is one in which you don't allow any heat to pass through. Okay. Okay. And so it's basically it's basically simulating a case where you surround that surface with styrofoam or something, and so it doesn't let any heat pass through. Okay. And so this is a special case of the last one where you're basically specifying a heat flow boundary condition, but you're just setting it equal to 0. Okay. But they separate it out just to be a little bit more convenient. Okay. And so it's the same logic of the reason why a fixed support boundary condition exists in ANSYS. Okay. And so a fixed support boundary condition is nothing more than a displacement boundary condition, but you just set everything equal to 0. Okay, so perfectly insulated is the same thing, and so it's nothing more than a heat flow boundary condition, but you just set it equal to 0. Okay. in reality, it's impossible to get a surface that's perfectly insulating. And so no matter, how good your thermal engineering is, if you have something that's hot, if you have something that's cold, heat's going to go from the hot thing to the cold thing. And so, you can insulate it as much as you can to try to limit the amount of heat that goes through, but there's always going to be a little bit of heat. And so, perfectly insulated is an approximation for sure. But in a lot of cases, it's very valid because the amount of heat transfer that can pass through an insulated surface is usually so small that you can ignore it compared to other effects. Okay. And so the next type of boundary condition is a convection type boundary condition. Okay. And so a convection type boundary condition models the effects of convective heat transfer. Okay. And if you don't remember what convection is, or if you haven't taken 407 yet, convection is just any kind of heat transfer that occurs to a moving fluid. Okay. Okay. All right, and so schematically it looks like this. So, let's say that you have your surface here, okay? And so let's say the surface of the solid is at some temperature Ts, okay? And then on top of the surface, we have some kind of moving fluid on top, okay? And so in most cases, this is some kind of air, okay? Or in other cases, it could be like water, like you have a water-cooled surface. Okay, or any fluid works. Okay, and so as long as the fluid is flowing, as long as it's moving, then you're going to have convection heat transfer that's occurring. Okay, and usually we use the symbol T infinity, and T infinity here denotes what's called the I call it the ambient temperature, or in other words, it's the temperature of the fluid. Where Ts here is surface temperature. All right. And so with all those things considered, the equation that we use to govern convection heat transfer is known as Newton's law of cooling. And so Newton's law of cooling states that, if you have a convection situation where you have, heat transfer to a moving fluid, the amount of heat that gets transferred is based on this equation. Okay. All right, so we have Q, and so little q here stands for heat transfer. Okay, and the units for this is watts. And that's as good. This is going to be equal to H times A times the difference between the surface temperature and the ambient temperature. Okay, so we have Ts minus T infinity. Okay. All right. And so let me go ahead and label the rest of the terms. So you already know Ts and T infinity. Okay. A here is the surface area. Okay. And so the surface area of whatever surface that you're considering. Okay. Where H here, H is what's called the convection coefficient. Okay. All right. And so the reason I bring this up is to, not to transform this class into 4.7, but, the reason I bring this up is, this equation right here is a really good place to visit so that we know how to prescribe a convection boundary condition in ANSYS, okay? Because in ANSYS, there's going to be two primary things that you're going to need to specify. And so you're going to specify H, okay? And you're going to need to specify T infinity. Right, and so I bring up this equation just to kind of remind you, what these parameters are and how they factor into the equation. Okay, estimating these values is kind of another story altogether, but we'll get to that on the next page. Okay. All right. Any questions on this? Okay. Okay. And so let's talk about how do we specify a convection type boundary condition in ANSYS. All right. And so if you want to specify a convection boundary condition in ANSYS, there's two, just like I mentioned, there's two quantities that we have to specify. Okay. So we'll do the easy one first, and then we'll do the hard one. Okay. Right. And so the easy one to specify is T infinity, where T infinity, remember, this is the temperature of the fluid. Okay. This is usually something that's known, and so you usually know this beforehand. And so, let's say that you're doing a thermal simulation on a car, that's driving on the 57 freeway. Okay. And so what the temperature of the air is outside because you have a temperature, you have a weather app on your phone, and you can just look up the temperature really easily. Okay. And so the temperature of the fluid is usually not that hard to determine. And so you can either use air temperature if you have like an outdoor application, or if you have industrial application, then knowing the temperature of the fluid is let's say you have water cooling or something like that. That's not that hard to determine. Okay. The more difficult one is H. And so H is the convection coefficient. And so intuitively or conceptually, what the convection coefficient expresses is how effective or how much convection heat transfer are we going to get. Okay. Or in other words, it expresses how good this fluid is at transferring heat. Okay. Which sounds easy in concept, but the amount of variables that H depends on is many and themselves hard to determine too. And so some of the factors that can affect H are things like the velocity of the fluid, so how fast it's going. Okay, let me say it depends on. Right, and so if your fluid is going faster or your fluid is going slower, then that's going to affect how good the convection is. Okay. Okay. It depends on what I like to call the nature of the flow, and so that's whether your flow is laminar or your flow is turbulent. Okay, and so it's going to depend on those factors as well. Okay. It's going to depend on the fluid material properties. Oops. Okay. And so some fluids are just going to be naturally better at transferring heat than others. Okay. And so if you have some kind of liquid metal, and so let's say that you have liquid mercury, for example, okay, That's going to be a lot better at transferring heat than just plain old air. Okay. And the main difference for that is like the thermal conductivity of the fluid. Okay. And the last one is the geometry of the flow, or I shouldn't say the last one, I said the last major one. Okay. And so whether your flow is going to be turning, or it's going to have some recirculation zones, or whether it's going to be hitting your part exactly. Okay. So the geometry of the flow is going to affect H as well. Okay. And so the unfortunate thing is that with the exception of this one, okay, with the exception of the fluid material properties, everything else here is incredibly difficult to determine. Okay. And in fact, for most cases, if you want to find out all of these flow quantities, you actually need to run a fluid simulation to get this. Okay. Okay. Which is not a trivial task. And so, running a fluid simulation so that you can run a thermal simulation is like peak complicated engineering stuff at its finest, right? And so it's not easy. Okay. And so, determining a good value of H is, I think, probably the most challenging part of running a thermal simulation. And if you've taken heat transfer before, probably you would agree is probably one of the more difficult things to do in just regular old heat transfer as well. Okay. And so I don't really have great advice for you in order for good ways to solve for H. If you feel strongly in your heat transfer knowledge and you want to apply like your concept from EGME 407, definitely this would be the place to do it. Okay. You can also run a CFD simulation to determine H. I've seen people do that before, and it's really cool. I haven't personally done it myself, and so I'm not actually sure how to do it. But I know that that's kind of generally the practice in industry. But of course, that takes a lot of work as well. Okay. And so if you're running a thermal simulation, the convection boundary condition will probably easily be the most difficult part, and the difficulty is going to be in determining what H should be. Okay. But if you can determine H, either through your own calculations or through you ran a CFD, or maybe you've gotten the information from literature somewhere, then you're golden. Then you're good to go. Okay. But determining this H is hard. Okay. Any questions on this? All right, so that's the convection type boundary condition. Oh, I didn't mention what type of boundary condition it is. Okay, and so a convection boundary condition, you can kind of make arguments whether this is a load or a constraint, but actually, because it has this factor of we're specifying this temperature right here, a convection type boundary condition is actually a lot closer to a constraint than it is to a load. Okay. Okay. And so it's actually possible to run a thermal simulation without any directly specified temperatures if you use convection type boundary conditions. Okay. And remember, because if you use convection, you're directly specifying what the fluid temperature is, and then that fluid temperature kind of translates to your surface. Okay. And so that's one of the nice things about convection is that it lets you it acts as a constraint for you in your equations. Okay. All right. And so the last boundary condition that we'll talk about is the radiation boundary condition. Okay. And so radiation, if you haven't taken 407 or if you forgot, radiation is the transfer of heat between surfaces through electromagnetic waves. Okay. It's the only form of heat transfer that doesn't require a medium, and so it doesn't require any material. Okay. Okay. And so that's how the heat from the sun, reaches the earth. Okay. And so, I've always hated the expression that people say, that scientists and teachers say, oh, without radiation, we'd all be dead because the sun's heat wouldn't reach here. That's true, yes. But, you can say that about a lot of things in science. And so, we can say that without airflow, we'd be dead. Without oxygen, we'd all be dead. It's like, yes, we get it. Life is complicated and it's a very complex, interconnected network. But without radiation, the sun's heat wouldn't reach us and we'd have no source of heat. And so, that's my grand statement about radiation. Okay. All right. And so the formula for radiation, I actually don't know if it has a name. I just call it the radiation heat equation. Okay, is given by the following. Okay. And so we have two quantities, epsilon times sigma. Okay. And it's Ts to the fourth minus T infinity to the fourth. Okay. And again, I'm bringing up the equation for radiation heat transfer just to kind of explain what you need to specify within ANSYS. Okay. All right. And so let's go ahead and label all of these terms. Okay. So TS is the same. So TS is the temperature of your surface. Okay. T infinity, this is the ambient temperature outside your surface. And so this kind of has the same definition as the T infinity for convection. Okay. Sigma here, let me get this dude's names right. Okay, so this is the Stefan Boltzmann constant. If you've had me before, I hate it when people name their scientific concepts after their names because this tells me nothing. Okay, but it only tells me that some dude named Stefan and his friend Boltzmann came up with this constant. Okay, and it's really important for heat transfer apparently. Okay. If I ever get smart enough to name a constant or name an equation, I'm gonna call it "fuck your name" equation or something like that. Because I hate it when.
Yes. Fucking amazing.
I'm not gonna put my name on an equation like that. Okay. All right. Anyway, it's the last week. I'm having fun. Okay. And so the last parameter here, and this is the most important one. This is the emissivity. Okay. Right. And so the thing with radiation is that a lot of it depends on how well your surface, or how effective your surface is at radiation, is determined by how well your surface can reflect light. Okay. And so this determines. So this is a constant, and so it's actually somewhere between 0.0 and 1.0. Okay. And what this expresses is how well your surface emits basically how well it emits light. Okay. Because there are some surfaces that are better at emitting light than other ones. Okay, and so this constant is basically a coefficient that determines it. Okay, and so on the one end of the spectrum, if you have an emissivity of 0, that tells you that your surface it basically can't emit any light. Okay? And on the other end of the spectrum, an emissivity of 1.0 means that your surface is really good at emitting light. Okay, and so physically, it's impossible to have exactly 0.0 and exactly 1.0 emissivity. And so most emissivities for most surfaces are somewhere in between. Okay. And the way that you look this up is that it's a property of your material. Okay. And so this is usually something that you can look up online. Okay. And so that's the radiation heat equation, okay? And so, you know, just like in convection, the two parameters that you directly have to specify are the emissivity, okay? So you have to specify how good your surface is at emitting radiation, okay? And you have to express the ambient temperature as well, okay? This is usually a little bit easier than convection because the emissivity is you know, there are a bunch of data, there's a bunch of tables on it. It's not flow specific, it's not geometry specific, and so that's usually something you can look up without any trouble. Okay, but with that said, you know, radiation a lot of times you know, is pretty negligible, and so for a lot of simulations, and you know, if you're taking 4.7, you know this too. For a lot of situations on Earth, we just neglect radiation altogether. Okay. And so, you know, unless you have some kind of space application, so if you're doing heat transfer on a satellite, when there's going to be no conduction, no convection, a lot of times you can leave radiation out of it, and it's not going to change your results. Okay. Right. And then just like convection, you know, because we're specifying this ambient temperature right here, radiation actually does count as a constraint as well. Okay. And in fact, you know, a lot of thermal simulations that I've seen on satellites, you know, they rely on the radiation boundary condition to provide a constraint because there's no other temperature that they can directly specify. Okay. All right. Any questions on radiation? Okay. All right. Actually, there's one more boundary condition. Although it's not technically a boundary condition, but it's kind of the same thing as standard Earth gravity. Okay, so I do want to go over it very quickly. Okay, and that's internal heat generation. Okay, and so internal heat generation, you know, just like you know, just like standard Earth gravity will apply to your entire body. And this basically expresses how if your body can actually generate heat on its own. Okay. Okay. And so, you know, I will say that this is not very common. And so, you know, the only situations where your body can generate heat is if you're if you have some kind of chemical reaction going on. Okay. Which is not all that common. Okay, but the option is there if you do want to do that. Okay. All right, and so before we jump into the sample simulation, let's just very quickly talk about what outputs you can view. Okay. And so I'd say there's two primary outputs that you can look at that are usually of engineering interest. Okay. Okay. And so the first one, of course, is going to be temperature. Okay. And so the temperature output, what this is going to show you is how temperature is distributed throughout your body. Okay. And so, of course, the temperature distribution, it'll be a literal heat map. Okay. And so I might have used that term, you know, throughout this semester about, you know, the equivalent stress field. It's a heat map. This is literally a heat map because it'll show you what the temperatures are. Okay. All right, and so the other type of boundary condition that we have is a heat flux, okay? I'm sorry, not boundary condition. The other type of output we have is heat flux, right? And so this tells you, how much heat or how much energy is entering or leaving your system at specific locations. Okay. And so this could be useful if you want to determine, where, if you have a situation with a lot of heat loss, this can tell you, where you're losing most of your heat. Okay. And so that can tell you, where you need to add insulation into your geometry. Okay. Okay. Any questions on this before we jump into the example simulation?
Professor.
Yep.
So the heat flux, is it an output? I thought it's just an input. It's like it's a load type input.
Yeah, so it's so you can directly specify the heat flux at certain locations, and so if you do that, that would be a boundary condition. It would be an input. But for all the places where you're not specifying the heat flux, heat is gonna enter and leave your geometry at those locations as well, right? Depending on what the temperature is there and what the temperature of the surroundings are. And so the heat flux output, this will show you, what locations in your model do you have, energy coming in and out in places where you didn't directly specify. Yep.
I see, thanks.
Yep. Okay, and so let me go ahead and switch to the computer. Okay. All right. Let me go ahead and bring up the notes, which I have here. Wrong class, but it's the exact same notes. Okay. All right, and so we're going to do a very simple simulation on a thermal fin. Okay. So if I can go ahead and scroll down, this is a situation that we're going to look at. Okay. And so we're going to have a cylindrical fin. And so we're going to have a directly specified temperature on one side. And so we're going to have a temperature of 100 degrees Celsius on one side. And the other side, we're going to have perfectly insulated. Okay. It's going to be cylindrical with a diameter of 5 centimeters. The length is going to be 100. And we're going to have radiation, convection, and all that good stuff. Okay. All right. I should have done this earlier, but let me go ahead and start up Workbench. Okay. We can go ahead and look at the example in the meantime. Okay. And so through this example, you're going to see kind of how I apply all the boundary conditions that we talked about before. Okay. Okay. Oh, one thing I forgot to talk about too is the material properties. And so while that's starting up, okay. Just like in structural simulations, you have to supply material properties as well. Okay. And the primary material property here is what's known as the thermal conductivity. Okay, so actually, let me go ahead and start this up. Okay. And so the thermal conductivity is a property of your material, which tells you, how effective that material is at transferring heat. Okay. All right, and so since we're doing a thermal simulation, we're going to go to the toolbox here, and we're going to click and drag steady state thermal. And so just like the name implies, we're going to do, this is a thermal simulation that's steady state, okay? And since I don't have the geometry prepared, we're just going to make it from scratch really quick. But it is just a cylinder, so it shouldn't take too long, okay? Okay. All right, so here we are in Design Modeler. Let me change the units, the centimeters, okay? So let me go ahead and go the XY plane. Let me go ahead and sketch, draw a circle. It's going to walk to this one. Okay. I'm not even looking at the right plane. This is the plane. Okay, sketching. There we go. All right, circle. There we go. All right, so we're going to draw a circle. We're going to dimension it. we're going to make this, what's the dimension? 5 centimeters. Okay. All right, we're going to go back to modeling here. Here is our sketch. And so I'm going to extrude this, create, extrude. And so we're going to apply this to sketch 1. We're going to add material, and we're going to extend this out for 100 centimeters. Okay, we're going to click generate. And there we have our cylinder. Okay. I'm going really fast just because, you know, we are almost out of time. But of course, but this is not something that you have to turn in. But, you know, if you want to follow along, you know, I just produced the cylinder really, really quickly. Okay. All right. And so now that the cylinder is created, I'm going to go ahead and close this out. And then we're going to jump into ANSYS mechanical. Okay. It's a little bit confusing because we still use the same program. And so the program is still called mechanical, even though we're running a thermal simulation now. Okay. And I'm just going to use the default material here, which is structural steel. Okay. And so actually, let's look at the material properties for structural steel while that's loading up. Okay. All right. And so we have structural steel right here. Okay. And you can see that the thermal conductivity here, which is, you know, how much heat can pass through, is 60.5 watts per meter K. Okay. And so this is a fairly moderate thermal conductivity. And so definitely on the higher side because it's a metal. Metals tend to have higher thermal conductivities than other materials. But, you know, it's not as high as like what copper would be. Okay. All right. And so just like we usually do, let me go ahead and change the units to millimeters. Let me make the element size here. Let's make it 1 millimeter. Okay. Let me go ahead and create this mesh. Yeah, that was a little bit too small. Oh yeah, that is too small. Stop. All right, so let me do 10 millimeters. Okay, and so here we have our mesh, and so we have we were fortunate enough to get a hexahedral mesh, and so this looks good. Okay, so now let's go ahead and apply our boundary conditions. And so if we go back to the figure here, okay, we can see that we have a specified temperature on one side, and then an insulated, perfectly insulated boundary condition on the other end. So let's go ahead and apply those boundary conditions. Okay, and so I'm going to go ahead and right-click on steady state thermal. We're going to go to insert, and then we're going to start with the temperature boundary condition. Okay, and so I'm going to click on temperature. Let me go ahead and specify the surface that I want to apply it on, and so I'm going to apply it on one of the ends of the cylinders here. Okay. And the temperature that we're going to specify is 100 degrees C. Okay. Okay. And so the next boundary condition we're going to apply is the perfectly insulated boundary condition on the other side. Okay. And so I'm going to right click on steady state thermal. Go ahead and go to insert. And then the boundary condition you want to highlight here is perfectly insulated. Okay. All right. So let me go ahead and click that. I'm going to go ahead and select that surface over there. Okay. And so that's going to prevent any, heat from escaping the other side of the fin. Okay. So we're assuming that the spin, no heat is coming out from the tip. Okay. All right. And so those are the two N-type boundary conditions. Okay. Now let's go ahead and specify the convection type boundary condition. And so remember, we're going to have convection heat loss from the sides of the cylinder, okay, from the sides of the fin, right? And so this is simulating the fact that, you know, maybe we have some air that's blowing over the fin, okay, and it has a convection coefficient of 0.5 watts per meter squared K, okay, and K, of course, here stands for Kelvin, right? And so in this case, you know, of course, I'm giving you the convection coefficient, and so it's you know, you can just plug it in. But most of the times this is not going to be given to you. And in fact, it's going to be very difficult. In fact, it's going to be a bit difficult to solve. But, you know, just because this is kind of a demonstration, I'm just going to go ahead and give the convection coefficient to you. Okay. All right. So to apply a convection type boundary condition, we're going to right click on steady state thermal. We're going to go to insert. Okay. And then we're going to go to convection type boundary condition right here. Okay. All right? And so you can see that the symbol for convection here is a fan, right? And so the fan is meant to symbolize some kind of airflow type boundary condition. Okay. All right, so we have convection, and so I'm going to go ahead and select the side of the cylinder, like here. Okay, so because we're having convection heat transfer off the side. Okay. Right. And so I'm going to go ahead and hit apply. Okay. And so you can see in the bottom, on the bottom left here, it's asking us to specify two parameters here. Okay. It's asking you to specify what the film coefficient is. Okay. And let me go ahead and switch the units. Okay. Right, because the units that I gave you the convection coefficient in are in watts per meter squared K, right? And so we want to make sure that we're in the same ones here. Okay, so I switched the units up here to meters. And so now we can specify the film coefficient in terms of watts per meter squared degree C, which is the same thing as K. Okay. Right, and so our film coefficient here is 0.5. Right? And our ambient temperature, which is the temperature of the air, this is 25 degrees C. Okay. All right. Any questions on this so far? Okay. All right, and so that's question.
Yeah, can you explain again how C is K this time?
Oh yeah. So C stands for degree C, and K is Kelvin, and so they both kind of share the same units. And so the way that you can convert between them is, I think, if you want to convert from degree C to Kelvin, you do 273 plus degree C is equal to K. Yeah. So K is a measure of absolute temperature.
Right.
And so if you have like absolute 0, that refers to 0 degrees Kelvin. Whereas degree C it's a unit system based on the freezing point of water. And so 0 degrees C is when water freezes.
No, yeah, I thought you meant that like the same degree of C could be the same for Kelvin. That's why.
Oh no, it's not.
Yeah.
So they are different, but the units are the same. And so watts per meter squared C is the same thing as watts per meter
Kelvin.
Kelvin.
Okay, cool. Thank you.
Yep. Okay. And so the last thing that we're going to specify here is the radiation boundary condition. Okay. And so let's go ahead and right click steady state thermal here. We're going to go to insert. We're going to go to radiation. Okay. And we're going to select the same surface that we did for the convection. And so it's and this is true in static structural as well. So it's actually perfectly fine to specify multiple boundary conditions on the same surface. Okay. And in this case, it makes sense because we're going to have both convection and radiation heat transfer from the surface. Okay. Right. And so I'm going to select the entire lateral surface of the fin. Okay. The emissivity here, we're going to set it to be 0.3. Okay. Because that's what it is specified to be in the problem. Okay. So we have epsilon here is equal to 0.3, and then the ambient temperature is going to be 25. All right, and so now that we're done specifying the boundary conditions, we can go ahead and specify our output fields. Okay, and so we have output fields of temperature and heat flux. And so let me go ahead and right-click solution A6 here, and so we're going to insert an output field for temperature. Okay, and so this is going to show us the temperature at all locations on our entity. Okay. And then I'm going to go right click solution A6 thermal, and then we're going to go total heat flux here. Okay. Right. And so this is going to express, how much heat is actually passing through our surface. Okay. Okay. And so now that we have all our boundary conditions and, we have all green check marks. So the only thing left to do now is solve. So I'm going to go click on the lightning bolt here. We're going to solve our model. Okay. And we get a temperature distribution that looks like this. Okay. All right. Actually, no, that's heat flux. All right. So let's look at temperature first. Okay. And so this basically tells you how much or how the temperature is like, throughout the cylinder. Okay. All right. And so on the left side here, you can see that we have a maximum temperature of 100 degrees C. Okay. And that's exactly where we specified our temperature, right? And so since we directly specified the temperature constraint on that side, It makes sense that the temperature there is exactly what we specified it to be, okay? And then on the right side, we can see that we have a low temperature of 47 degrees Celsius. Okay? All right, so let's look at the heat flux. Okay, and so the heat flux again is an expression of how much heat is being in this case is escaping from the fin. Okay, and so since our object here is at a higher temperature than the surrounding fluid, right? Because remember the surrounding fluid around here is only 25 degrees C. Okay, since our fin here is a higher temperature, right? Since our fin is a higher temperature, and I totally messed that up because my hand is next to the edge of the lectern here. Okay, since our fin is a higher temperature, this tells us that heat is going to escape, right? Because remember, heat always goes from hot stuff to cold stuff, right? Right, and so this heat flux here tells you the magnitude of how much heat is being lost from the fin. Okay, right, and so you can see in this region right here, we have the most heat loss, right? And so we have a heat loss of about 8,663 watts per meter square, right? And that makes sense because our temperature is the highest over here, right? And so since the temperature is the highest here, the difference between the surface temperature here and the fluid is greatest. And so that's going to lead to the highest amount of heat loss, okay? And then as you go down the rest of the fin, then the temperature or the heat flux decreases, okay? Okay. Any questions on any of this?
Can you show like an internal generation term on this cylinder as well?
Sure.
Thanks.
Yeah. So if you want to add internal generation, you can right click steady state thermal and you can go to internal heat generation. Okay. And so the only thing that lets you select here is an entire body, and so it's very similar to standard Earth gravity. And so we're going to apply it on the entire geometry here, okay? And we have to specify the magnitude of our heat generation, okay? And so this basically expresses how much heat is being generated in our solid per volume, okay? And so I'm just gonna let me do something big actually. So let me do 100 watts per meter cubed, okay? All right, and let's see how that affects our solution. Right, and so with this boundary condition, we're saying that we're generating 100 watts of power per meter cubed of our structure. Okay, that actually didn't do much. Let me go ahead and increase this. Let me increase this to 10,000. Okay.
So in structural problems, we have like the body force instead of the thermal generation term, right?
Exactly. Right. Yep.
Is the body force the same as the gravitational force on the on the structure?
It is. Yep. Or I should say the gravity force is a type of body force, and so there's other body forces that you can include, but gravity, of course, is the most common. And so the other body forces that you can have are things like electromagnetism, and so electromagnetism is a force that's felt throughout the entire body, and so that's another example. But probably the most common one is gravity, because gravity is a force that's felt throughout the entire body because it's a field effect. And so because we're standing in a gravitational field, every particle of our body feels that gravitational force. And so internal heat generation is the same thing. And so when you're generating heat, we assume that every particle on the inside of this structure is generating heat. Yeah.
Got it. Thanks.
Yep. Okay, and so we're out of time, and so that's a very quick introduction to thermal simulations. And so I think we spent more time reviewing 407 than we did talking about this. But if you understand kind of core concepts in heat transfer, and you just apply the same process, the finite element process that we've been going over in this class in ANSYS, it's kind of just a very natural marriage between those two ideas. Okay. All right, and so thank you guys for coming today. I know everyone's kind of really stressed with the final week here, but I always appreciate you guys coming out. And so when we come back on Thursday, we're going to do CFD simulations in ANSYS, and so that's hopefully that's going to be exciting for you guys. Okay? So have a great evening, everyone, and I will see you for our last class session on Thursday.
Bye, Dr. Tran. Thank you.
All right, bye, Jasmine. Have a good day.
You too.
Thanks, Dr.
Bye.
Tran.
Bye, Stephen.
Thanks again.
Thanks, Chris.
So let's go on up to like post on the project. There's a PDF right next to it.
Yeah, that's perfect. Yeah,
Is this thing to do like using?
Yeah.
Okay, so
Yeah.
that's like a good enough, just the calculations, right? There's an intro to like describing it and do that
Yeah.
after, right?
Yeah,
Okay.
yeah, that's perfect. Yeah,
And I think.
you can blow it up for the whole page. That's
Okay, cool. Cause yeah, I think that's ANSYS gave me like, I don't know, it was 200 or more, or 200 less PSI.
wow, that's pretty good. You got pretty close.
Yeah, and then I have another question. I have a, so this is like a simulating soap dispenser and rotating pole.
Yeah.
Sit like 100 pounds.
Mhm.
I got like 456. I don't know if I'm getting it wrong,
Mhm.
but ANSYS, you know, like, I don't know if it was 200. It's like double, and like I was like, crap, I don't know if I could get close enough. So I was just trying to change it. I was wondering if there's like a way to do like a section view, so you can apply boundary conditions inside a
There is.
solid object.
There is, and so there's a way to kind of split an object, and actually I can show you really quick on this one actually. And I showed this for my grad student, and I actually didn't know this before this year too, so I kind of just found this out. And so let me just go to geometry here. Oh shoot, do I remember how to do it?
No, that's cool. I just like figured out something. Cause yeah, I did try like changing the geometry or just literally cut the object in half
Yeah,
and simulate that, but it's a different. I got different results.
I see, I see,
So like towards the corner of it's now the stress area instead of the bolts where the bolts bolt
I see. Yeah, so I think so. I'm basically gonna do the same thing where I'm gonna split this model in half. Gosh, how do I do this? Split surfaces from faces. So let me do, what point is that? ZX. Oh, shoot, okay. I think that is what I want. Oh, shoot, did I have something for my grad students? I don't know. Yeah, I did a demo of it in the class. How did I do this? Shoot, I don't know if I wrote it down. It might have just been a video.
No, it's cool. Just search it off.
Yeah, I can. Let me give you the because it was for their midterm project, which
Oh,
they
I
wanted
see.
to know. And what was the midterm project do? Midterm project do E10. Yeah. Shoot, it was one of these lectures in.
Okay, no worries. It's fine.
But yeah, I think if you search on YouTube like split a surface in ANSYS,
Section view.
then yeah, then it's not that hard. It was like a 5-minute video on YouTube. That I
Oh,
found
okay,
before.
okay.
Yeah.
But I have another question. So like,
Mhm.
let's say like your really hand calculation is like way off to the answers is like a bad thing.